Recording is rolling. It is Wednesday, January 15th. All right, so first, a few announcements from the school. Well, you guys are getting your lab and lab write-up out because we're going to do that in a few minutes, but school stuff. All right, so 2 days from now on Friday, there's Club Picture Day and also Senior Panoramic. Uh, so I know in the past they usually fit this somewhere in first period, so I'm guessing that's how it's going to play out. So if you're a senior, all right, now, yes, dress for success. I got email. The principals put together a principals council. Here, let me show you guys what this email looks like, so you guys can read it with me here. All right. So, now, if you're interested in this, zoom in here. Says, "Good morning. I'm looking for students to serve on an advisory council for me. Goal is to get a cross section of students to participate, so I can have a wide view of student issues and possible solutions when needed." So I'm guessing maybe she's looking for students from different grades and different levels, maybe some AP, some honors, some regular. I will meet monthly with the council and discuss upcoming DHS events policies, anything else they would like to discuss, thinking in advance. All right, so there's from the principal, Ms. Legate. So if that's something you're interested in, you can let me know, and I might put your name in a recommendation for that. All right. All right, what else we got? Of course, there's a 3-day weekend coming up. It's Martin Luther King Day. All right, so all right, keep that in mind. Guys, then, I forgot to write this on here, but I've been writing this last few days anyway. Guys, what do you have? What do you guys have that's due on Tuesday and then Wednesday? Yeah, your AP classroom progress check, right? You guys know that? Yeah. There's also some textbook puzzles that we haven't quite gotten to yet. I think I'll probably also. Whoa, did my screen freeze? What's going on here? We've got a delay going on. Okay. I think I'll probably have these two after the weekend. I think would be good too. Right. And I'll also get you guys another take-home quiz coming up soon, but so one day at a time. We got Wednesday, Thursday, Friday this week. Okay. All right, so we're gonna finish this lab. We need to put together that graph. Say, how do you interpret that graph? Okay, and then I'm gonna have you guys score your AP write-up. Right, AP style write-up. We'll do that. Okay. You guys remember I flashed this on the screen or handed these out, so you guys had that to work from. Yeah. All right, and then I got some notes for you guys. We're gonna be doing. Oh yeah.
For analysis, you don't have to redraw the graph on the back, or you just have it on
Just the graph. Yeah, the graph can be analysis. That's fine. Right. I gave you guys a graph space. I gave you guys some axes. So as long as you have the graph, right? So there's your analysis, or the main part of analysis. There might be a few calculations in the mix. All right, so we find what we worked on yesterday. So you got a back from each class here. All right. Actually, you know what might be helpful is if I do a real fast recap of what we did. I know some of you guys were absent yesterday. Oh, let me rewind. Oh, this right here. So here's the setup. There's this PVC pipe system. I've taken it down since yesterday, but it was low friction, so it could rotate about the central axis. Hung on different lab weights, so sort of the independent variable was whatever lab weight. Right? And this would slowly accelerate down. I had some of you guys time with the stopwatch, how much time. We fill out this table, some measurements, some calculations, and ultimately our goal is to figure out what's the rotational inertia of this rotating pipe system about the central axis. There you go. There's a real fast recap. Right. Right. What we were able to do, we measured what's the radius of that central pipe, what's the mass system hanging, right? What's the falling distance, right? Right, which was 70 centimeters all the way down, right? How much time did that take? Okay. Did 3 trials, right? And then the rest of these columns were calculations. So if you know how far it falls as a function of time, and starting from rest, you can use this first kinematic formula to figure out what's the linear acceleration. If you know the linear acceleration, you can divide by the radius of the central pipe to get the angular acceleration of the rotation, because it was speeding and spinning. Okay. Tension was pretty much the weight. Now, technically, it's elevator physics, m times g minus a. We derived that class 2. Right. Right. So then, and then torque was r cross f. Right. Like we got an r cross f going on here. Okay. And we're about to put together this graph right here. So torque equals I times alpha. Right, that's Newton's second law in rotation form. Right? And look exactly what I gave you on this set of axes. I gave you torque versus angular acceleration. Okay. Torque in Newton meters, angular acceleration in radians per second squared. Okay. That's what we're going to put together right here. You guys ready to make that graph? I shall probably just put it on this page just to blow it up a little bit bigger. Okay. Okay. So I got torque in Newton meters on the vertical axis. I got angular acceleration and radians per second squared on the horizontal. Okay. Okay. And these are going to be Cartesian coordinates. So we're going to have 1, 2, 3, 4, 5 coordinates. Okay, you guys remember this? 5 coordinates. We're going to have. All right. Okay. All right. So who wants to volunteer the coordinates you found? All right, Alec. Okay. So let's scale these. Like, how big can this go? What's the biggest torque? Alec, what's the biggest torque we have?
Biggest torque is 0.538.
You said 0.0538?
Yeah.
Okay. So 0.0539. Okay. 39. All right. Now that's Newton meters. So attach that. Right, that's that what we got? Yeah, something like that. So maybe I should scale it like that. So maybe we should go 1, 2, 3, 4, 5, 6, maybe. Let's go 1, 2, 3. Here, ignore that number for a moment. I should 0.0539. I shouldn't have done that. 1, 2. Okay, 1, 2, 3, 4, 5, 6. Here, yeah, pretend I didn't write that yet. 0, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06. Okay, and 0.0539 is probably right about here-ish. Okay. What's the largest angular acceleration from yesterday? You said 0.65? 0.67? Radians per second squared? That looks about right. Wait, is there another zero in there? Is it 0.067? Or is it 0.67?
Yeah.
Okay. All right, let's go with that. All right, so let's do 1, 2, 3, 4, 5, 6, 7. Okay. So 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and then 0.67 is right about point there. Okay. All right. Now those two values you gave me, the torque and angular acceleration, is that a pair that go together? Yeah, that would make sense, right? The largest torque would correspond to the largest angular acceleration. Okay, so that's bam. All right, we got a point on the board. I'll go ahead and label that coordinate so we know what we're looking at. So 0.627 radians per second squared, and then 0.0539 Newton meters. There you go. Got one coordinate on the board. Okay. All right. Of course, we're going to plot all the other ones. Do you guys remember from yesterday, or I think you can reason this out, what shape this graph should look like? Here, here's what formula is probably going to go with this, right? Torque equals I times alpha. That looks linear, right? Linear? Okay. And hopefully the slope of this is the answer to the question, what's rotational inertia? I think. I don't know. We're going to find out. Okay, so, Alec, what's another coordinate on this graph?
0.453.
0.453?
And 0.043.
0.043. Okay. 0.453, 0.043. Okay, that's rad per second squared and Newton meters. Okay. All right, what else you got?
0.317.
0.317.
And 0.0326.
326. Okay. Rad per second squared, Newton meter. All right. What's the next one?
0.147.
0.147. All right.
0.0214.
214. Okay. That's rad per second squared, Newton meter. Okay. And what's the last one?
0.048 and 0.062.
48, 062.
16.
Okay. 0.048 and 0.6062.
16.
Oh, 16. Oh, oops. Okay. 0 point, sorry. That one. 0.16. That's more like right here. Oops. Okay. 0.048, 0.16. Okay. Rad per second squared. All right, and Newton meter. All right. There's the 5 points. Okay. Okay. Now, to do a line to best fit, guys, line to best fit, should I connect dot to dot to dot to dot to dot, or should I hold my ruler and sweep it? Nice straight line through all of them. Yeah, how about that last thing I said? So there you go. Feel it like that, right? You think? Okay. Okay. Now, ooh, wait a minute. I wrote this formula, torque equals I times alpha. Okay. That doesn't exactly line up with the graph. That's okay. This is actually leading towards something. Okay. Guys, what's sort of the difference between this equation, well, what I wrote at the top here and this line? They don't exactly match because what? Huh? What's going on with the graph? It doesn't exactly show up with this equation.
The line doesn't intersect at 0.
Yeah, it doesn't go through the origin. Okay. There's a y-intercept. Okay. So how could I modify this to match the actual data? Plus what?
It would be minus if you try to.
Well, okay, so plus because it's all shifted up something, right? Right. Okay. Plus what? What it looks okay, yeah, you could put a number on here, but uh, what concept is this on the y-axis? Torque, right? And what type of torque? Like there is some definite y-intercept right here. Okay. What does this torque represent? What kind of torque are we talking about? Torque due to what? Friction. That's what I'm looking for. Friction. Right. So I'm going to do a y-intercept. I'll call it frictional torque here. Right. Here's how you can figure this out. Maybe some of you guys figure this out. Okay? You might remember this yesterday. I only made this mistake in this class. Is I put on a live weight that was too small. I think I started with a like 100 grams. I think I did, and that wasn't quite enough to move it. I put on 100 grams, and the whole thing didn't even move at all. You guys remember that? Okay. Now, if there was truly zero friction, then it definitely would have. It would have accelerated. Okay, but it didn't. Okay. So it takes some minimum amount of torque to get it to rotate at all because it has to overcome the little friction that there actually was. Yeah, that's what this is right here. This right here is, I'll call it tau FR, a frictional torque. You guys see that? Right. Now, once you overcome that frictional torque, right, anything addition goes into its motion. Hence, everything else is a straight line. So it's this right here. Okay. Okay. All right. So now this is the equation in terms of variables, maybe more like a formula. Okay. Let's get some numbers on this. So an exact equation for this. So I'll say torque equals, right? Okay. And then, well, alpha could be the sort of y-axis variable, or sorry, x-axis variable. So that's the same place. What about this I? Could that be the slope right here? And this frictional torque could be the y-intercept. Okay. So let's do rise over run. And so this rise over this run. So I'm gonna calculate this out here. I equals. Okay. Now if I pick 2 points and then do rise over run between these 2 points. It looks like these 2 points pretty well lie on my line. So I'll take these 2 points right here. Okay. So is that change in torque over change in angular acceleration? Right? Delta y over delta x kind of thing. Okay. So what's this here? Oh, really trying to make that stand out. I'm going between these 2 points right here. So what's this change in torque and this change in angular acceleration? Okay. So change in torque. That looks like, okay, I'm running out of paper, so I'm just gonna do this on my calculator screen. Okay. So change in y value, I got 0.0539 minus 0.0214, right? You see the change in y values right there? Okay. So I did this minus this. Okay. Throw that in parentheses, then divided by, and then this run right here, which is this minus this. So 0.627 minus 0.147. Okay. So change in y over change in x. Okay. change in tau over change in alpha. Okay, that's giving me 0.068. Okay, and then guys, what's the unit attached to that number? Kilogram meter squared, because this is a rotational inertia. Okay, or if you did, okay, yeah, however you get that. Okay, okay, so go back up here and make an equation. 0.068, and that's kilogram meter squared. Okay. And then multiply that by angular acceleration, which is variable. Okay. Then plus, and I got this frictional torque. I'm gonna just kind of guess. Does that look like maybe, I don't know, maybe 0.011, maybe somewhere? It's a little bit above 0.01. 0.011, and then I'll call that Newton meters. Okay. So that right there is the equation of that line, which describes everything that was going on yesterday. Okay. Like you could put on different lab masses, give different torques, it would have different angular accelerations, but they all lie on that line.
And just a coincidence that that's the radius.
Oh, yeah, because it's completely different units, right? Yeah. So it has nothing to do with it. Yeah, go on. All right, you guys good with that? Okay. All right, so now, you guys have the answer to this box then? Look, what number goes in this box? Yeah, 0.068. Right. Now, yesterday, do you guys remember I was referencing that rotational inertia table? We're looking at just the geometry before I even said anything in motion. I said, well, here's my sketch from yesterday, exactly what I did in class. Okay, so got this T pipe system. I said, well, the central axis might be providing a little bit of rotational inertia, but it's probably mostly from these arms that are out horizontal. Okay. So I did like either 1/3 ml squared times 2 or 1/12 ml squared for the whole thing. Okay, however you did. You guys remember yesterday I got 0.037 kilogram meter squared? It says probably a lower bound. It's probably something a little bit more than that. Okay. And oh, look at this. The actual answer we got out of this was 0.068. Yeah, that's kind of in the ballpark, right? It's definitely same order of magnitude, right? And it's a little bit above my lower bound estimation. Yeah, so that was right. I mean, if it was crazy different. It was like 3.5 kilogram meter square. You know, that'd be like way off. But yeah, it's pretty close, right? Like I said, all lines. All right. All right. So you guys ready to score your write up? All right. So I have a 12-point rubric here. Okay. So you guys remember yesterday I had this on your desk. Okay, so we got question, measuring equipment, procedure, which involves the setup. Procedure involves a few things. Briefly describe the setup, what measuring tool to use for what variable, identify what's independent, dependent variable, and what are you controlling. Okay, and always mention this detail: multiple trials to reduce experimental uncertainty. The version we did in class yesterday was I had different students tell me their stopwatch times, and we made believe that was unique trials, but right. Analysis is usually graphs, but it could be equations if you're trying to solve for something, okay? And then come up with a conclusion that answers the original question. Right? All right, so what was on your desk yesterday? All right, so actually I did give everybody the question, which is what is the rotational inertia of the pipe system about its central vertical axis? Okay? So everybody had that question. Okay. Measuring tools. Here's what I came up with. Maybe you mentioned a scale or a triple beam balance, something to get the weights. Either a roller or a meter stick. I was definitely using a meter stick. Okay. And a stopwatch or a timer. I had you guys use the stopwatches. Okay. Now, if you have known mass values, you can get away with not mentioning the scale. If you didn't mention the scale, it's probably the least important one. But you definitely had to mention the meter stick and the stopwatch. Okay. Or if you said roller and a timer or something, that's a good thing. Okay. All right. So, procedure. All right. 1 point for describing the setup. And I have a real brief description here. Set up the pipe system to rotate about its vertical axis. Tape a string to the vertical central axis of the pipe system. Wind the string around the axis. Route the string through a pulley so that a lab weight can be suspended and allow the lab weight to fall vertically, causing the pipe system to rotate. That's the entire setup. That's it. Right? A few sentences right there. Right. That's where we got a picture of this. That's somewhere over here. Right. Here it is. Right. So that's that was the setup I had yesterday, right? All right, so give yourself a point if you describe the setup. Sounds pretty good. All right, next point. And this is going to add up to 12. All right, so when you guys hit this FRQ, it always adds up to 12 points. So I try to do that if I can. Using the scale, measure the mass of the lab weights in kilograms. All right, so, okay, so you know the mass of the lab weight. But tell you what, if you mention the lab weights at all, go ahead and give yourself a point. AP might not emphasize using the scale if they're known values. So if you mention the lab weights, just go ahead and give yourself a point for that. Okay, next point, using the ruler or the meter stick, because I used a meter stick, measure the radius r, the central vertical pipe. Record that radius. Yeah, guys, you have to know the radius of the central pipe because the string wound around that central pipe, okay, this radius feeds into the torque equation. Like if you don't know the radius of the central pipe, you can't know what torque is acting. Right? Is that true? Right. Guys, if I had a wider pipe, because I had a pipe that was about pretty close to 1 centimeter radius, guys, what if I had a big old pipe? Would that be more torque or less torque? More torque, because torque is R cross F. Right? So whatever the weight was, or the tension in the string was the force. Right? Yeah, if I had a wider pipe, that would be more radius. That'd be like a bigger torque. Right? Kind of like putting the doorknob opposite of the hinges. You get a wider door that you can press. Right? Next one, using the ruler and the stopwatch or meter stick and stopwatch, measure the falling distance and the corresponding time that the lab weight falls. Right, so I just put a collective point there. Yeah, I think I'm trying to get these out to 12, right? But you need to measure the falling distance and also the corresponding time with the stopwatch. Okay, so got a point for that. There's repeat 3 trials per lab weight. Right? That's always a point on this when you get to the FRQ. That's always a point to do multiple trials. In fact, you know what I could have written out now that I'm looking at it again is to reduce experimental error. Right? They might be looking for that too. Right? Like, well, why are you doing these multiple trials? Oh, to reduce experimental error. Sometimes you're a little fast with stopwatch, sometimes you're a little slow. Right? And then next point, you have to identify, well, what are you changing? What are you sort of treating as an independent variable? You guys remember I had different lab weights and I was changing out lab weights. So repeat the process using lab weights, 5 different masses. There you go. Right. So I got different lab weights going on. So maybe 5 different lab weights, 3 trials each. So came out to like 15 trials. Right. Everybody right so far? So far. Right. All right. So far I've got 6 points. All right. Next, analysis. Now, in this analysis, I also included the calculations. You guys remember we made some measurements. That's what I've done so far for the procedure. And then we did some calculations and then the graph. The calculations in the graph I'm putting all in the analysis section, okay? Because AP would probably do the same thing. Okay. But however you categorize this, as long as you have this somewhere in your procedure, then you're good. Right? So determine the average linear acceleration of the lab weight falling. Hey, and that was you guys remember this first kinematic formula? That was that application. So if you just wrote the formula, guys, if you wrote x equals 1/2 at squared, solve for a, that will check off that point right there. Okay, see, acceleration is 2x over t squared, which again I gave you guys because I printed it right above the table. It says a is 2x over t squared. But for AP, you would have to show where you got that from. So you have to write the first kinematic formula and rearrange it with algebra. So 2x over t squared gives you each acceleration. That's a point. Next point, determine the tension in the string for each lab weight. Of course, there are different tension. Right? So each lab weight was associated with the tension. Now, this one, I've seen AP kind of skip over, like gloss over this detail a little bit. Sometimes they just use the weight itself. That's not strictly true. Really, you have to go to elevator physics. You guys remember elevator physics from yesterday? Where do you have this in the? Well, okay. So here, get this a little closer here. You guys read this. Okay. So net force is mass times acceleration. I would start with Newton's second law. I say, well, the net force is the weight down minus the tension pulling up on the lab weight. You can rearrange this. You're going to get the tension as m times g minus a because it was accelerating down. M times g minus a. Okay. So that was one step. We had to figure out what's the tension in the string. Right. Now, since it was accelerating so slowly, it was pretty much the weight anyway. Right. But if it was accelerating more quickly, then you would definitely have to take this into account. Okay, m times g minus a. Okay, guys, good. Right. Now that's the linear. That's the tension of the string. So we got the linear acceleration of the lab weight. We got the tension of the string. Okay. And we're able to do something else with that linear acceleration, which is figure out the angular acceleration of the whole pipe system. So that's this alpha right here. Right. So alpha, that's a over r. Hey, that's turntable physics. You guys remember that turntable physics poster that was referenced in yesterday? Okay. So if you know the linear acceleration and you know the radius of the central pipe that string was wound around, you can figure out what's the angular acceleration alpha of that whole pipe system speeding up, rotating. Right? So there's a point.
Is that where it can come from?
Huh? Yeah. Let me find it in my PowerPoint here. Where's it's this right here. You guys remember this? Okay. So guys, if you have a turntable turning, isn't it true that let's do all these. How far does a point move on the outside? Well, let's theta times r. Right? So the more it turns times its location from the center. Okay. In fact, a specific guys, what's a specific version of that top formula that you guys have known since elementary school? If you go all the way around the circle, circumference equals 2 pi r. Because this theta is in what unit? Radians, and 2 pi radians gets you all the way around. Okay. So then if you take a, I know some of you guys are in calculus, if you take a time rate change of that position, you get to velocity, and velocity time rate change of that turns into acceleration. Okay? And we were using the bottom one right here. That's what we just used. Okay? Take a, divide by r, that gets you back to alpha. Okay? So this, and I'm calling this a turntable, but in the lab yesterday, that application, this is a cross section of that central vertical pipe. Okay? Maybe have a string wound around that. Same thing. Okay. All right. Next, determine the torque. Right now, torque is r cross f. So if you know the radius of the central vertical pipe, it's about 1.1 centimeters. Okay, multiplied by the force, which is the tension in the string, that gives you the torque. Right, and then these last 2 points right here, torque and angular acceleration. That's what created coordinates that went on that graph that we just put together earlier today. Okay. Alpha and torque. Okay. So next point then is graph each of the 5 points on a graph. So torque versus angular acceleration. That's like y versus x. Torque versus angular acceleration. Tau versus alpha. Okay. And then last point, because torque equals I times alpha. Well, okay, and then we also had an intercept for that side. Okay. Rotational inertia is represented by the slope of that graph. AP especially likes you to look at graph properties like this, okay? Because here, so like, I got a trickier question for you guys. Okay, let me kind of sketch this out real fast. So you guys know we put down 5 points and basically got a graph that looks like this, right? Right. So it was torque equals I alpha, and then it was plus this frictional torque right here. Okay. Because what if instead of doing 5 points on the graph, because it was like 1, 2, 3, 4, 5, it looks something like, kind of like that, 5 points. Right? What if you just picked a single coordinate and you said, well, I'm just going to do torque equals I times alpha. I'm going to feed this torque and this alpha and into this equation, and I'm just going to solve for I that way. Okay? Guys, if you did it that way, you would get a slightly wrong answer. Would you be slightly overestimating or underestimating the rotational inertia with that method? Here, so let's say it again and get a show of hands. What do you guys think? Okay. So what if instead of plotting 5 points on a graph and getting the slope, which is what we just did, okay, what if instead you said, I'm going to pick a single point, like this point right here, bam, just that point, and I'm just going to plug it into this equation, torque equals I alpha. I have torque, I have alpha, I can solve for I, boom, done. Okay. Well, you could do it that way, except you would be slightly what? Overestimating or underestimating the I. Let me see, show of hands. How many guys think if you do that method, you'd be underestimating the I? You think you'd be overestimating the I? Yeah. Okay, I see a bunch of hands on that. How did you know you'd be overestimating? Yeah, because the line would be too steep. Because if you just plug in this equation, you would be assuming that it goes through the origin. And then, you guys see how I'm holding my ruler right here? Okay, so from the origin to that point, that would be a steeper line, wouldn't it? Which would be like a greater I than it actually is, right? And so AP really likes to look at graph properties for considerations like that. Okay. And so rotational inertia would be the slope of tau versus alpha. what we did today. Right? And then conclusion, make sure you answer your question. Okay? Because I've seen a lot of lab write-ups in the past where by the time you get to conclusion, you say, well, what does this have to do with the question? You have to start with. You guys know the question was, what's the rotational inertia of the pipe system about the central vertical axis? Right? And so you come up with a number here. What do we get? Like 0.06 something kilogram meter squared. Right? All right. All right. So you guys get there? All right. Do you guys score yourself out of 12? All right, so score yourself out of 12. So like we normally do it, I'll create a non-graded column in the grade book. I'll put that there just so you can reference it, so you can know how you're doing on these lab write-ups. All right. All right. So I got a few more slides on this PowerPoint. Let's go over this PowerPoint because I haven't quite yet gotten to rotational kinetic energy. That's the last main concept I got to do. All right, let's do a review of what we've done so far. I'm going to flash these slides fairly quickly. Guys, this is a psychology thing. It's just how human brains work. Every time you see something, your brain gets a little bit better. Okay, so you guys remember turntable? Actually, we talked about the turntable. You guys remember that? You guys remember rotational kinematic? Okay, I think the quiz I'm about to get you guys in the next few days, I'm going to ask some rotational kinematic questions. Can you guys navigate these?
Sure.
Right. So something turns, like how far does it turn? How fast is it turning? Okay. Okay. Yeah. How much time? Okay. Could you guys give these rotational kinematic graphs for a turntable? All right. Here's slowing to a stop. Here's what these graphs look like. Slowing to a stop. We did this last semester. Okay. Center mass weighted average. Right. Okay. Got some stability. There's a little bit bonus slides here. Right. You guys remember rotational inertia? So something to do with mr squared. For a single point, it's mr squared. Okay. For a more complex shape, it's the aggregate of mr squared. Okay. And then if you take calculus, you can prove each of these red formulas. Okay. Okay. All right. Parallel axis theorem. AP is bringing in this year. So guys, I know for sure you're going to be asked this on the AP exam because AP is reintroducing this topic. They haven't asked this the last few years, but they are this year. Could you guys get a ball rolling across the floor? Say, okay, if it's a basketball, it's 2/3 mr squared from this table, plus an additional mr squared because it's actually rolling about that point down the bottom. Could you guys do that? Right? Gives you 5/3 mr squared. Right? So you could get that question on the AP exam. Okay. Torque, R cross F. You guys remember R cross F? Turning a wrench, opening a door. Okay. Right hand rule. Sorry, actually, AP is not going to ask this. All right. So you'll see this in college. College, you'll see this. If you go into engineering, you'll see right hand rule. All right. You guys also matrices in college. I showed you a matrix the other day just to introduce you to the concept, but you might have to study that more in college. Okay. But AP sticks to clockwise, counterclockwise instead of all this stuff. Okay. All right. Equilibrium. Guys, what's your equilibrium conditions? What goes to zero and what else goes to zero? Force and torque. Right. And then that's also true along each axis. There you go. 2D, 3D. Right. Guys remember seesaw back on Thursday and also yesterday. Guys, did I solve the unknown mass of the pipe yesterday by using exactly this method? Right. And I did all throughout my classes yesterday. I got like pretty much the same number all yesterday. Right. Scaffold. Did you guys solve the tension in each spring scale? Okay. That was your Friday lab. Ooh. Right. That was good to know. Yeah, you have to go through torque to solve that. This is a classic physics question, ladder laying against the wall. This is a classic one. That was a warm-up question recently. Okay. All right. This puts a bunch of concepts together. R cross F results in I times alpha. Right. So variations in that question you could be asked. Right. That was yesterday's lab. Right. Okay. That was all review. Okay. Just so you can see all the. Sorry, we got some more review. So here's a new one. Okay. You remember angular momentum? This is I times omega, which is analogous to m times v back last semester. You guys remember collision physics, collision carts? Right. P equals mv. Now we got L equals I omega. Right. And that's also conserved. A really classic example is ice skater. Right. You pull your arms in. Right. Guys, does it take some work to pull your arms in? Take some work? Yeah. That energy comes from your muscles, turns into mechanical energy. Okay. Okay. Now what's conserved is this angular momentum. So I times omega. You decrease your I, you therefore increase your omega. Spin faster. Okay. I forget if I asked you this. Because which has more mechanical energy? The picture on the left or the picture on the right? More mechanical energy. The picture on the right. Because that energy came from doing work by pulling your arms in. It's difficult to pull your arms in, force times distance. Okay? And take a guess. What do you guys think the formula is for rotational kinetic energy? This is the last concept I haven't hit yet. Exactly. 1/2 I omega squared. Right? Which is analogous to 1/2 mv squared. Right? So 1/2 I omega squared. Okay. So you say, okay, well, the I went down and the omega went up, but that omega is being squared, so it counts more for the kinetic energy. In fact, AP might ask you to explain that in sentence form, exactly what I just said. Right? Say, well, angular momentum is conserved for the ice skater, so why does kinetic energy go up? You could say, well, there was work done by pulling their arms in. That could be an explanation. Or you could say, well, the omega, the fact that it's being squared, it counts more. Ooh, okay. Okay. Spin a basketball. I know I've asked this as a midterm question in the past. Okay. So this puts some concepts together. So torque times time results in a change in angular momentum. This is analogous to impulse from last semester. You guys remember hitting a ball with a bat? Okay. It's like force times time results in a change in momentum. Right. Right. So I put a torque on the ball by bam, hitting it at the edge, bam, 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 right, get it spinning. I know from the rotational inertia table for a basketball, it's 2/3 mr squared. It's like a spherical shell. Right? I can solve for how fast does the basketball rotate? Right? Right. Guys, this pair of graphs right here, you're going to see on the AP exam. So no, this is the same relationship. Right? So if you put a constant torque for some time, it's going to be spinning faster, 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 got an angular acceleration. So there's going to be building up more and more angular momentum. Right? Now this graph on the right, angular momentum is a function of time. Okay, that's building up more and more and more. And the slope of that graph represents the torque that you're putting on it to get there. Right? Guys, these two graphs tell the same story from different perspectives. Right? Guy standing on this hill, guy standing on this hill. They see some event a little bit differently, but it's the same story. Okay. Did I ask you guys this? Guys, what if you were increasing the torque? What if the torque was a diagonal shape? What shape graph would be on the right? Parabola. This L versus T would be a parabola, right? Right. I've seen AP ask that question before. AP also likes to ask this question about every year. Rotational inertia disk. So you lower one disk onto another. What's conserved is rotational inertia. So L is conserved. Right? You guys see this gold line plus this green line add up to this red line for every single moment, right? So see, they're going to stick together. It's going to get the gold disk spinning, and it's going to slow down the green disk at the same time. Okay, like that. All right. AP likes this one. What's the rotational inertia associated with a point mass? How does that make any sense? Okay, so you take your regular momentum, mv, cross it with this distance r from this pivot point up here. Suppose this is a blob of clay and it sticks, and then they start rotating. How fast are they going to rotate? So that'd be omega. Maybe you're solving for omega. Well, the angular momentum comes from this r times this mv. Right? That's the source of the angular momentum. Okay? And then if they're rotating, there is a combined I. You guys see that I right there? It's kind of deceptive because it's really the rod plus the blob of clay that's now stuck to it. So maybe you have to add together like two different I's. Okay. That's like a combined I right there. And then they rotate how fast, and then you can solve for that. Okay. All right. All right. That was all review so far. You guys seen all the slides. All right. Here's the last few slides. You guys ready for some new stuff? All right. Rotational kinetic energy. All right. So what can you solve with that? Actually, if we go way back, let's go way back at the beginning. All right. That's it's right here. Guys, this is very bottom line. You see K equals, back in linear days last semester, 1/2 mv squared. Now it's going to be 1/2 I omega squared for a rotating disk, or maybe a rotating ball, something like that. All right. So it look like, all right. So what can you solve with this? No, I got the same puzzle solved maybe two different ways. Do you guys see the same setup here? I think this is actually one of your textbook puzzles. Maybe there's a pail hanging from a disk that's rotating. No, guys, this disk, importantly, does have mass and radius, so it does have rotational inertia. Last semester, we tended to ignore that. You guys remember those Atwoods from last semester? We just ignored it. Well, it's such small mass, it doesn't really matter. Okay? Or sometimes I would say massless, frictionless, but that's not true anymore. Now this disk has rotational inertia. Okay? Now, you could ask a number of questions. You could say, oh, how far does this pail fall in some amount of time? How fast is it falling after some amount of time? How far does it how fast is it falling after some distance moved? You can ask all those questions. Okay? And there's two different approaches now. Now, here's one approach, is you could go through a free body diagram, and you could go through rotational dynamics. Right? I have a bunch of individual formulas here. Got torque, so R cross F results in I times alpha. I got elevator physics here, right? What's the tension in this rope? Minus mg results in ma. Here, I got turntable physics here. And oh look, this 3 kinematic formulas linear, and for the pail, say moving straight down, and 3 kinematic formulas angular for this this disk rotating, right? And they all fit together, right? Kind of like yesterday, right? The linear acceleration of that weight falling was related to the angular acceleration of the whole pipe system rotating, okay? Right? And then you could approach it that way. Right? Now, there's one specific question you could get where it's easier to solve in terms of energy, right? Which is the next slide right here. You guys see the next slide? It says sum of energy initial equals sum of energy final. Right? Now, I'm going to scroll back to, okay, because you guys know the next setup I want to solve in terms of energy, right? I want you guys to guess. Guys, what specific question do you think you can very easily answer with an energy approach? Right? Okay, and think about the formulas that are involved. Guys, if I'm talking about energy conservation, do you ever see time as a variable in energy questions? No. So it's not going to be after following some time. It's going to be after following some what? Some distance, right? Okay. And what do I want to know after following some distance? Do you ever, in an energy equation, see anything about acceleration? No, although there might be acceleration, but that's not a question. It's not in the energy formulas. What do you see? Velocity. That's the question. If you ever see the question, how fast is this pail moving after some distance fallen? That's a perfect setup for energy. Okay, so now I'm going to scroll this side right here. Sum of energy initial equals sum of energy final. Okay. Now you guys got to identify what energies we're talking about. Say if the pail starts from rest and it's going to follow some height change. There's your height change. So mgh. Okay. That's like the supply of energy, mgh. Where does that energy go? Okay. Okay. So after it falls some distance h, right, which maybe I should label that in a picture, but you guys can imagine. Falls some distance h. Okay. Well, now that energy's gone into two places. The pail falling has some 1/2 mv squared. Right? And actually, if that's all there was, that would just be back to the Galileo question. Galileo drops balls off the Leaning Tower. Right? Right. But don't forget, now there's this disk that has some rotational inertia. Here we go. Here's the first application. You guys have seen this in this class. 1/2 I omega squared. You see that right there? And that's also sort of demanding some of the energy also. You see that too? Right? So here's your supply of energy. The pail falls, mgh. Right? Where does that energy go? It goes into moving the pail 1/2 mv squared, plus also rotating the disk 1/2 I omega squared. Is that? Right? Right. There's your setup. Right. I think it's one of your textbook questions. So see if you guys can get this from scratch on a blank piece of paper. I'm just showing you guys how to solve it here. Okay, go. Probably Tuesday, I think. Just yeah, Tuesday. Okay. And I think we'll just have a bunch of stuff to do on Tuesday. Okay. All right. Next step, guys. Is this V related to this omega? However fast the pail is moving is related to however fast the disk is turning. In fact, that relationship is turntable physics. You guys see for omega, I just subbed in V over R is being squared, so V squared over R squared. Is that great? That's turntable physics. Okay. What else? Do you guys think this I, guys, if this I is a cylinder shape, do you think it's 1/2 mr squared, right, for a cylinder? And go back to the rotational inertia table. For a disk, it could be 1/2 mr squared. Right. Now, I did not put that on this poster, but that could take the place of this I to be 1/2 mr squared. You guys see that? Right. Okay. And when I say M, I'm talking about the M of the disk, not the M of the bucket. Okay. Okay. And here's how fast it's going to be moved. Okay. You could also solve for how fast is this rotating, but that would be if I subbed out the V instead of solving out the yeah. Okay. All right. Got just enough time. I got a few more slides left that all kind of look like this. All right. So I got a ball rolling downhill. Now, just like with the pail falling, this ball rolling downhill, there's two ways to solve it. See, I'm toggling between two different ways to solve it. Right. So the hard way, I think, is going through torque, and the easy way, I think, is through energy. Okay. Okay. Maybe let's start with the energy because I think this would be the way I would do it. I would say energy is conserved. Guys, what type of energy at the top of the hill? Potential energy, mgh. So I jot down mgh. Okay. By the time the ball gets to the bottom, does the ball have a linear like this point in the middle? The ball has a linear speed. If you point a radar gun at it, that's 1/2 mv squared. But also the ball is rotating. So isn't that also plus 1/2 I omega squared? Right? Right. And guys, is this V related to this omega? Yeah. And I did that substitution. The next line. You guys see for omega, I subbed in V over R. You guys see that? Right? I skipped a few algebra steps, but by the time you get to the end, you can get the linear speed of the basketball as a function of this drop height. Okay, good.
Is that the radius, the point on the ground and the ball, or is that?
Yeah. Yeah, guys, this R right here is the radius of the ball. R is the radius of the ball. Yeah, is that? Okay. Now, for a basketball, which is a spherical shell, so all the mass is on the outside, this is the specific solution. But if you change out the ball, Guys, what if I change it to a solid ball? You guys see this bowling ball, the solid all the way through? You guys see the answer changes a little bit because it has a different rotational inertia. So the answer is a little bit different. Okay. Now, let me go back to the hard way to solve it. Come on here. Sorry, my screen's all kind of messed up. Okay. But if you solve this through torque, you also have to bring in the parallel axis theorem because you have to consider, well, the ball's actually rotating about the point at the bottom. Notice for energy, I didn't have to consider that. I could just plug in straight 2/3 mr squared straight from the table. But for the torque analysis, I actually have to consider the 5/3 mr squared, okay? Because parallel axis theorem, right? Okay. So whether or not you consider parallel axis theorem depends actually on the method that you use. Okay. Okay. You guys see this one's more complicated, but it leads to the same answer. You guys see that? Okay. So there's a spherical shell, like a basketball spherical shell. Okay. Here's a solid ball, right? Which could be the same process, but different rotational inertia, so a little bit different answer. Okay. Okay. And then here's a like any ball. It just got some general eye, right? So whatever type, right? Something like that. Hey, you guys remember the other day? The day I was asked on head jury duty, I assigned you guys some videos, right? And they had an animation like this, right? To tell you a sort of secret, I have a secret suspicion. They've been stolen from me because I never actually seen this. I thought, oh, it's my original idea. I've been to AP conferences and shared my book around and sold a few dozen copies of that. And then, oh, I see this show up as an animation. I wonder if they stole that other book. I don't know. Maybe not. Okay? But guys, the fact that each of these has a different rotational inertia type, even if they're different masses and different radial sizes, does not matter. The M and the R cancel out. If you look back the last few slides, the M and the R cancel. It has to do with how the mass is distributed. So if you have a bowling ball next to a marble, which would both be solid, I bet this would both tie. They would both end the same. Okay, guys, this ring where all the mass is distributed far out, it has a lot of rotational inertia per unit mass and per unit range. It's gonna lose the race. Okay, so the more concentrated the mass is towards the center, it's gonna win the race. The more spread out the mass is, it's gonna lose the race. Okay, all right. All right, you guys have a good day, and see you guys tomorrow. Oh yeah, okay, this hockey puck, yeah, if you put it on its side, yeah, it would be that cylinder. Yeah, and they would tie. Right. The deal with the hockey puck is it's the only frictionless lane. So the frictionless lane is gonna beat everything. Because there's no rotation. Okay. All right. Boing, boing.
You're returning to the lab.